There are some other variant in terms of conductor technologies that were introduced along the way, but they have very limited success, including gap conductor. The gap conductor is simply leveraging what we call installation technology that drives down the sonar knee point so that you can manage the overall or sag in the conductor. However, the gap conductor is very difficult to install, and it is impossible to repair if there's a breakage because the core would be retracting inside from the breaking point. And there's also the grease that are inside the gap that often leaks to the surface, which creates a hydrophobic surface. And those grease sometimes, when there's high temperature from the environment, that they would drip down and it drops into cars and buildings that people don't like it. In terms of INVAR conductor, which is really take advantage of the low thermal expansion of INVAR steel. And by the way, INVAR is very expensive. It is also a magnetic material. And when you look at circuit design, electrical engineering, INVAR has significant inductive impedance because of that magnetic behavior. And by the way, INVAR steel has a very low strength, which means they have to pair up with high temperature aluminum alloy that has very poor electrical conductivity. And so INVAR conductor, if you were to compare it with ACSR, they are a very lossy conductor, and they're rarely used. For example, in the US, we've never seen INVAR conductor used in our transmission grid. There are also other composite core conductors in recent years. I will cover probably the so-called multi-strand conductor, like Tokyo Rope or C7. These products, there's the industry perception oftentimes that because they have 7 strands in the composite core, there's a redundancy in there. That is a false perception. Because when you have, let's say, 4 out of the 7 strands broke, and you still have 3 strands left, yes, you may have some remaining strands, but that is not redundancy, because the composite portion of these multi-core conductor will only have, let's say, 40% of the strands left. That is no different than a monolithic composite core that has partial damage to it, that you got 50%, 40%, or 60% strands left. So that false perception of redundancy is absolutely not true. And at the same time, you also have the same challenge in terms of bending vulnerability, because the fundamental limitation of unidirectional composite, that compression failure, because the compressive strength in a unidirectional composite is only about 60 to 70% of the tensile strength. That's why it always fails in the compression side. That is still present. And when you have multi-strand, the composite material that is furthest away from the neutral axis, which is where you are suffering from the most compression stress, that is actually higher because it is further away from the neutral axis compared to a monolithic core. So that problem is actually worse than what we might perceive as, well, you got small core there, it's more bendable. And lastly, there are challenges associated with fittings. Imagine if you use crimping approach, and if you do not have enough crimping because you are sensitive about damage in the composite core, you will always leave that middle core loose, and you are not going to get the full strength out of it. If you crimp it too hard, you also get into the other extreme, which is the composite core have point contact between them, and you could be crushed in the core when you crimp it too hard. So these are very practical issues, And on top of that, there's the cost consideration because you had to make 7 smaller strands and then recombine them into a composite core compared to a monolithic approach that is easy to manufacture and you can control that cost in a much more effective way.